Hey everyone, so now that we've done a lesson, I like to start off class with these review board questions. They're in your notes package, so you can do them before, and you should do them before, and I'll just go through all of them. So pause the video now, go through all those questions, and then you'll see how I can go through them now. So let's start off. So to respond to any question by supplying an answer as a vector quantity, the student must include. So if it's a vector, you have to include both the magnitude and the direction. Okay. Two people are dragging a canoe across a level beach using light ropes. Person A applies a force of 40 newtons. Person B applies a force of 80 newtons. And there's a force of friction. What's not shown in here, that's 100 newtons. That's 100 newtons force of friction. What is the net force on the canoe? So F net is just going to be, I'm going to make these positive and these negative. So it's going to be equal to the force applied from A and the force applied from B minus that force of friction that we have acting on it. So it's going to be 40 newtons plus 80 newtons minus 100 newtons. And 40 plus 80 is 120 minus 100, and that's going to give us 20 newtons. It's positive 20 newtons, so that's going to be 20 newtons forward. So C is the correct answer. What concept or principle best explains why the cab of the truck is often separated from the load by a steel barrier? So if this truck comes to a stop, what's going to happen is this load here is going to want to stay in motion, right? Newton's first law says that objects in motion stay in motion. So if there's not enough friction between here, this load will keep going and it'll go through the cab, and that would be not good. So that's why they have the steel barrier to protect the person inside of there. So Newton's first law is the best way to explain that. Force of friction would be an okay answer, but we're looking for best explains, and the fact that objects in motion stay in motion would be the best answer why you need that steel barrier. How far is it from Camrose to Drumheller if it takes 2 hours and 10 minutes driving at an average speed of 84 kilometers an hour? So to do this one, it's just a simple V equals D over T question. We want to find a distance. So our time, you have to be the same. So 2 hours and 10 minutes. So it's going to be 2 hours and 1/6 of an hour. That's going to be our time. That's how you do that. And then the speed is 84 kilometers per hour. The hours cancel out in there. So what I would do, how I would type that into my calculator would be, I would go 2 plus 1/6, like that. And then I would multiply that by 84. And I get 182 kilometers, which makes D the correct answer. For number 5, the force of tension in a string attached to the object shown is equal to the force of gravity. Which of the possible situations could happen? So Ft is equal to Fg. So that means that our F net is equal to 0. And anytime our F net is equal to 0, it means it can be either stopped or moving at a constant speed. So the object is moving at a constant velocity up, for sure, that can happen. The object is moving downward at a constant velocity? Yeah. The object is stationary? Yes. All three of these situations can happen if our F net is equal to 0. A student on her daily exercise plans runs at a velocity of 1.2 meters per second north for 3.5 minutes and then walks an average of 0.3 meters per second for 5 minutes. Her average velocity during this time interval is... Okay, let's do this one. So to find our average velocity, it's going to be our total displacement over our total time. That's how we solve this question. So let's draw out what happens. So a student on a daily exercise plan runs a velocity of 1.2 meters per second north for a time of 3.5 minutes, and then walks an average velocity of 0.3 meters per second north for a time of 5 minutes. So we want to find our average velocity. So we need to find a distance in here. So we're going to use v equals d over t. And we have meters per second in minutes. So my speed is 1.2 meters per second. And my time is 3.5 minutes. So I want to switch that to seconds. So I'm going to put minutes on the bottom, seconds on the top. So it cancels out, and there's 60 seconds in 1 minute. Okay, same thing with this. My speed is 0.3 meters per second. And then my time is 5 minutes. And there are 60 seconds in 1 minute. So that's how I would solve for the distances of both of those. Okay, so for the first one, it's going to be 1.2 times 3.5 times 60. So that's how far I go. And then the second one, I go 0.3 meters per second, and I need to go 5 times 60 in brackets. Okay, so that's my total distance there. So my total distance is, so both are north, so positive 252 meters and positive 90 meters. So that's my total distance. And then all my answers are in meters per second, so my total time is going to be that 3.5 minutes times 60 seconds in a minute, and then I need to add that to 5 minutes, and there's 60 seconds in 1 minute, because I want to be in seconds. Okay, so to do this, I'm going to take, my top is going to be this plus this, and then my bottom is going to be 3.5 times 60. I'm going to add that to 5 times 60. And that's how I'd want to do my brackets if I want to do that all in one. And then that's my average velocity. It's a positive answer, so it's going to be 0.67 north, which makes B the correct answer. Okay, so that's stuff from last lesson. So let's do types of forces. So when objects fall near the surface of the Earth, they are attracted to Earth because of the strong gravitational field around it, around the Earth. Earth has a large mass, so it has a strong gravitational field. The strength of the gravitational field has to do with the mass of Earth and the distance you are away from the Earth. So if this is the Earth, this is the surface of the Earth, so this is us standing on the surface of the Earth, what that means is that the average radius of the Earth is 6.37 times 10 to the 6 meters. So no matter where you are, you're going to be the same distance away. And what that means is that the gravitational field is the same. And our gravitational field at this point is 9.81 meters per second squared. So no matter where you are in the Earth, the average gravitational field is 9.81 meters per second squared. So since you're roughly the same distance from the center of the Earth anywhere you are on the surface of the Earth, the acceleration due to gravity is the same, and the acceleration due to gravity near the surface of the Earth is 9.81 meters per second squared. So if you go to another planet, there will be a different gravitational field due to the fact that those planets have different masses, and then they have a different radius, so you'd be a different distance from the center of that planet than you would be for Earth. So for example, the acceleration due to gravity near the surface of the moon is 1.6 meters per second squared. So the moon has a much smaller mass, and you're actually a little bit closer, but the smaller mass makes it a much smaller acceleration due to gravity. So you need to know the difference between mass and weight. So mass is the amount of matter in an object. Just how much stuff you have in you. It's measured in kilograms, and it's the number on your driver's license. So it says weight on your driver's license, WT, but it's actually mass. So this is difficult to change quickly. Now, weight is different. In everyday life, mass and weight are interchangeable, but in physics they're not. So what weight is the force due to gravity acting on an object. It's measured in newtons, and it can change based on what planet, roller coaster, elevator you are on. Okay, so weight is caused by the force due to gravity acting on an object. So to calculate weight, we can use this formula where Fg equals force due to gravity or weight. M is our mass, and g is our acceleration due to gravity near the surface of the Earth, which is 9.81 if we're talking about the Earth. So on your formula sheet, because it's a force, you can find it under forces and fields, and it's just this one right here, Fg equals mg, so that's where it is on your data booklet. So let's do an example. So a 100 kilogram object is stationary on Earth's surface. Determine the force due to gravity on the mass, the object's weight on the surface of the Earth, the object's mass on the moon, and the object's weight on the moon. So let's do all those. So we will use our new formula, Fg equals mg. Okay, and the first one is asking for the force due to gravity on the Earth's surface of the mass. So we have a 100 kilogram object. G is 9.81 meters per second squared. So that's really easy to calculate. That's just going to be 91 newtons. So what that is the force due to gravity on Earth. Okay. So the second question asks for the weight. So you have to remember that this is the weight. This is the mass. So if we found Fg, we found the weight. So the weight is 981 newtons. That's the weight. They're the same. Mass of the object on the moon. Well, mass is the amount of matter in the object. So if you're 100 kilograms on the Earth, well, you're going to be 100 kilograms on the moon. So this is your mass everywhere. But the last one's asking for the weight on the moon. So that's when we have to go our 100 kilogram mass times the acceleration due to gravity on the moon, which is 1.6 meters per second squared. And if I multiply those, I end up getting 160 newtons. So that is your weight on the moon. Okay, so that's how you do those questions. So what is this weight on the moon, weight on the Earth? What does that mean? Well, I can show you a video here. So this video shows the difference between the weight on the Earth and the weight on the moon. So when you're on the moon, you feel light. And when they walk on the moon, they skip. And you might have done this if you're in the water. If you're in water, you kind of skip when you walk along the ground because you feel lighter, because you no longer have just the force of gravity. You have the buoyancy of the water lifting you up. And when these guys fall down, they do fall down, which is dangerous. You can see how they get up, right? Because they feel light, because they're only 160 newtons. They feel 1/6 of their normal weight, but their mass is the same. They still have the same amount of matter in them. So let's do an example here. So we have a 1,300 kilogram boulder sitting on a level surface. Determine the normal force acting on that boulder. So let's draw a free body diagram. Anytime we're trying to find forces, we should start with a free body diagram. So let me switch my cameras here. So here's our boulder. When I draw my free body diagrams, I like to put the mass in there. And it's on the Earth, so there's a force of gravity acting on it. And because it's stationary, Well, there must be, oops, that's a little bit off my screen. There must be an equal force acting on it because the net force is 0, so we draw an equal area, an equal arrow. So because we know these are the same, we can say that Fg is equal Fn. We don't have a formula for force normal, but we do have a formula for Fg. We can break this down and say that Fg is equal to mg. So mg is going to equal this, but it's also going to equal this because they're the same. So I just have to go 1,300 kilograms times 9.81 meters per second squared. And I can find that force normal. So if I do that, and I go 1,300 times 9.81, I end up getting this. So this has 4 sig digs, but as long as we're using this, we have 3 sig digs, so we'd want to answer to 3 sig digs. So my force normal would be 1.28 times 10 to the 4 newtons, and this would also be 1.28 times 10 to the 4 newtons. So both of those would be 1.28 times 10 to the 4 newtons, and that's how you'd solve that question. Okay, so let's do a board question. So a 1.2 times 10 to the 3 car is driving east at a constant speed of 75 kilometers per hour. To maintain the car's speed, the engine applies a 4.5 times 10 to the 2 Newton force east. Draw a free body diagram of the forces acting on the car. Determine the weight of the car. Determine the force of friction acting on the car. And calculate how long it will take you to drive 300 kilometers. So pause the video. Try these on your own. I'm going to go through them right now. So you need to try them on your own first. So I'm going to start off with my free body diagram. So I have my car, which has a mass of 1.2 times 10 to the 3 kilograms. It says that there's a force applied to maintain the speed of 4.5 times 10 to the 2 newtons. And it says that it's moving at a constant speed. So if it's moving at a constant speed, well, there must be some other force, probably force of friction. And that force of friction is going to be the same. There's also going to be a force normal and a force of gravity that are the same because it's going at a constant speed. It's not accelerating in any direction. And it's really important with free body diagrams. Don't put speeds in there. If you put a speed in there, don't. Only draw forces in free body diagrams. So ask us to determine the weight of the car. The weight of the car is just going to be mg. So 1.2 times 10 to the 3 kilograms times by 9.81 because the car is on Earth. And we can find the weight of the car. So we go 1.2 times 10 to the 3 times 9.81. And we get we get 11,772. So we would want it to be 2 sig digs in the question, so 1.2 times 10 to the 4 newtons would be the best answer. And you could even put down, but if it's just asking for weight, we know it's down. Okay, and then determine the force of friction acting on the car. Well, the force of friction, because it's moving at a constant speed, is going to be the same as the force applied. I already drew that in there. The friction, 0.5 times 10 to the 2 newtons. Right? And we can say west, because the car is going east, so it's backwards. And then calculate how long it will take the car to travel 300 kilometers. Well, that's what we need our speed for. We can use v equals d over t. Move the t up top, move the v down below. If we go 300 kilometers at a speed of 75 kilometers per hour, then we can calculate how long it's going to take. So we would go 300 divided by 75, and we get 4 hours. We have 2 sig digs in the question, so 4.0 hours would be the best answer. Okay, that's that. So friction. We calculated friction already, but friction always opposes a motion, so it's going to go opposite the direction of our motion. And the smoother the surface, the less friction there will be. So you can see why friction happens, because there's tiny little grooves in it, and it just helps slow it down. So there's two different types of friction, which may seem weird, but there is. So the first type of friction keeps an object stationary. So what keeps this block stationary in the incline is called a static coefficient of friction, or static friction. And kinetic friction is what slows down objects that are moving. And the weird thing is that those frictions are different. So on this dog, there's kinetic friction because it's sliding, and on this block that's stationary, there's static friction, and they're going to be different. Okay, so I can show you this. So if I have a whiteboard here, and I have this eraser, right? And then I increase my incline. So it's keeping it in place right now as a static friction, right? And then it can only go to a certain incline, and then once it starts moving, well, then the coefficient of kinetic friction takes over, and that's going to be different. So I'll explain that a little bit more. So it's always harder to start something moving than to keep it moving. So what that means is that static friction will always be higher than kinetic friction. And we have this little graph here, and I can show you what this graph means, but let me just do a little demo for you. So what I have here is I have a little spring scale, and the harder I pull it, the further that goes back, and then I just have it hooked up to a 3-hole punch. So right now it's stationary, right? So the force of friction is holding it in place, but at a certain amount of force, that the force applied is going to become too big, and then it starts to move. So what I want you to notice is what happens to this reading once it starts moving. So, So the force gets bigger and bigger and bigger, and now moving at a constant speed. Right? Let's see that one more time. So it jumps up, and then once I get it moving, it only needs about 2 newtons of force to actually keep it moving, but to start it moving, it needs about 4. So it's harder to start it to get moving than to keep it moving. That's what I wanted to show with that. So that's what this here is saying, right? So I increase the force, my force of friction is equal, right? So I apply 10 newtons of force, or actually, I guess with this one, 1 newton of force, 1 newton of friction, right? I increase it even more, or not 1, let's say this is 2, and this is 2. And then right at about 4, that's when it starts to move. So this point right here on the graph, we call our threshold of motion. So that's just when it starts to move, but it isn't quite moving yet, but it just starts to move. And after that, the force drops down, and the force to keep it moving is much lower than the force to start it moving. Okay, we'll do some questions, you'll sort of see what I mean by that. So this is a video on ABS brakes that talks about how they use this technology of static friction over kinetic friction.
During emergency braking or on slippery surfaces, a driver may apply braking force that is greater than the tyre's capacity for grip. If this happens, the wheels can lock up, causing the vehicle to skid out of control. By preventing this lockup, the vehicle stops sooner and remains under the driver's control. The anti-lock braking system, or ABS, provides this assistance. So, how does it work? Sensors on each wheel constantly measure their rotational speed. The ABS control module samples this data continually, comparing the rotational speed of each wheel. If one or more wheels is rotating slower than the others, a condition that will bring the wheel to lock, the system takes action. It instructs the brake master cylinder to direct brake force away from the locking wheel, so it releases and regains traction. As the wheel begins to turn again, braking force is momentarily reapplied. This process is repeated up to 20 times a second and causes the characteristic pulsing feel through the brake pedal. As a result, the driver's intended brake force is applied without locking up and skidding, allowing the driver to maintain steering control while braking, meaning that stopping distances may also be reduced. The vehicle on the left has ABS. The vehicle on the right does not. Both vehicles are traveling at 100 kilometers per hour. Let's simulate an emergency braking situation and see what happens. Both drivers apply their brakes at the same time and with the same force. But the vehicle with ABS maintains control while braking and is able to steer around the obstacle. ABS helps a driver avoid accidents by preventing lockup and loss of traction. This allows the driver to maintain steering control during heavy braking and may help to reduce stopping distance.
So the formula for force of friction is this right here. So force of friction, and then this is kind of new and weird. We know force normal, we know force of friction, but this is weird. So FF is the force of friction, FN is the force normal, and that weird little letter is called mu. It's a Greek letter, and it represents the coefficient of friction, and it doesn't have any units. So this formula can be found on our formula sheet. Oops, where did I put that formula sheet? So because it's a force, it's under here, and it's just a second one there. Force of friction equals mu Fn. So I'll explain what the coefficient of friction is. So coefficient of friction is just the ratio between the amount of friction and the amount of normal force. So coefficient of friction has no units because they cancel out, right? If we go back here and we move force normal under here, well, this is in newtons, this is in newtons, so the newtons on top, newtons on the bottom would cancel out. So the higher the coefficient of friction, the more grip there is. So everything has their own coefficient of friction. So this is steel on steel, copper on rubber, wood on wood, Teflon on glass. These have their own coefficient of friction. So you'll always see that the static coefficient of friction is higher than the kinetic. It's always going to be harder to start it moving than harder to keep it than it is to keep it sliding. Right? That's what all these values show here. You don't have to memorize them. They're not on your data book. I'll give them in a question, or you'll try to find them in a question. So let's do an example. So a 2 times 10 to the 3 Newton sled is stuck in the snow. Someone is pushing on it with that force until the instant before it starts to move. That's key. Instant before it starts to move. Find the coefficient of static friction. So these questions will always be set up like this. So we have a sled like this, and it tells us it's a 2 times 10 to the 3 Newton sled. So that's just referring to, let me just make this a little bit thicker there. That's just our weight. So our weight is 2 times 10 to the 3 newtons. That's our Fg. Okay, which also means that our force normal is equal to 2 times 10 to the 3 newtons as well. So it says someone is pushing on it with a force. There's a force applied of 2 times 10 to the 2 times 10 to the 3, or 2.5 times 10 to the 3 newtons until the instant before it starts to move. So it isn't moving yet. So that means that our force of friction is going to be the same as the force applied. Okay. So if we want to find our coefficient of static friction, that's this scenario. So we usually put a little s here if it's static, and we just put force normal over there. So our force of friction is going to be the same as our force applied, 2.5 times 10 to the 3 newtons. Our force normal is the same as the force of gravity. And when we calculate that, we get, oops, didn't mean to do that. So 2.5 times 10 to the 3 divided by 2 times 10 to the 3. And we get 1.25 as our coefficient of static friction. Okay. So if we want to do the second part of this, the sled is now moving, same sled, is being pushed at a constant velocity of 4.5 meters per second with a reduced force of 2 times 10 to the 3 newtons. So what is the coefficient of kinetic friction? Well, now it's moving. So let's draw a free body diagram for when it's moving. So it's the same sled, so it's going to have the same weight. So Fg is 2 times 10 to the 3 newtons. Force normal is 2 times 10 to the 3 newtons. My force applied is less, it's 2 times 10 to the 3 newtons, and it's moving at a constant speed, so it's 2 times 10 to the 3 newtons for my force of friction. Force applied, everything's the same. We use the same formula, but this time it's kinetic because it's sliding. So we move force normal under there, and if we calculate this, my force of friction is 2 times 10 to the 3 newtons. 2 times 10 to the 3 newtons is my force normal, so it ends up being 1.00 as our answer. And it's the same sled, but the static is always going to be higher than the kinetic. And that's what we saw with this graph here. Oops. Right, static is the highest, that's the threshold of motion, the size force, and then it goes down for kinetic. And that's what we saw in the little demo I showed you as well. Okay, so to finish it off, we have a board question here. So pause the video, see if you can do it, and I will do it right now. A force is applied to a 5 kilogram object to move it at a constant velocity. The static coefficient of friction is 0.8, and the kinetic friction is at. Determine the magnitude of the applied force. So to do this question, draw a free body diagram. So we have a 5 kilogram object. There's an applied force. It's moving at a constant velocity. So there's a force of friction, those are equal. There's a force of gravity here, which is just going to be mg, so let's calculate that. 5 times 9.81 meters per second squared. And that's going to be 49.05. So this is 49.05 newtons. So that means that our force normal is 49.05 newtons. Okay. We have our did I not? There we go. Sorry. I think I was drawing all that out and I didn't have that on. So that's our force normal, that's our force of gravity. This is our free body diagram here. Everything's equal. Force of friction equals mu Fn. So we can find the force of friction with this. So they give us 2 coefficient of frictions in this. They give us static and kinetic, but if it's moving at a constant speed, we have to use kinetic, which is 0.70. Our force normal is 49.05. So we can find our force of friction. And if I do that, 0.7 times 49.05, I get 34.335. And we know that it's moving at a constant speed, so if this is 34.3 newtons, then this is 34.3 newtons. And I have 2 sig digs, so it'd just be 34 newtons would be my final answer. Okay, using the free body diagrams and the formulas to help you. Okay, so this is a homework, not too much. So we have some friction stuff, some weight and normal force stuff, and that is it. If you have any questions, let me know.